Here is a project. You will design and implement a Quasi-Newton method that uses partial information of the Hessian. Let's consider an unconstrained optimization problem, minimum of x, of f of x. It can be solved iteratively starting from an initial point x0. The gradient descent method is formulated as in this equation. From the old iterate, negative gradient scaled by a parameter gamma will be added to get a new iterate. For this method, you have to choose this parameter gamma very nicely. Once it is large, then the algorithm may be oscillatory or diverge. If it is too small, then the convergence will be very slow. For the Newton method, the formulation is given in this equation. From all the iterates, we are trying to get the correction vector like this. Rather than negative gradient, we apply the inverse of the Hessian to get the correction term. And now, usually for Newton method, we don't need that 1. The gamma can be 1, and to get the update to get a new iterate. The Hessian is defined here. Okay, now let's see some remarks. For large problems, the computation of the Hessian and its inverse is computationally expensive, occasionally becomes impractical. Wherever applicable, the Newton's method converges much faster than the gradient descent method. And if we start with some good initialization, so that there must be a neighborhood. So if we start within the neighborhood, then Newton method will converge quadratically with the parameter 1. That's well known. Once you try to solve quadratic problem, then just a single iteration makes the minimizer. So that after one iteration, it converges completely. So it is a really good method. The problem is the computation of the Hessian and its inverse can be quite expensive. So let's see one example here. Now I implemented the code in Python. That is now by using SIMP package, we can get the gradient symbolically quite easily for given function. And now for each variable, this is collection of variable. For each variable, like x0, x1, x2, and we can get derivative, partial derivatives, and collect them as a vector and return that is gradient. Now, for this second function, this function is trying to get the gradient and Hessian simultaneously. First, we try to save the gradient into G, and for now G, we make a derivative, and for each component, we make also such derivative, one more derivative, so it becomes Hessian. So this function returns the gradient and Hessian simultaneously. Now symbolically, we found this gradient and Hessian, so you have to evaluate the gradient and Hessian once a point is selected as in this formula. Once you find, for example, now Hessian symbolically, then xk is a numeric vector, then you have to evaluate this metric as a numeric values, including all numeric values. So that is evaluation function. Evaluate, the mathematical formula is given, and for the variable, now this is numeric value. Then here, by using the substitute, the function, we can get the evaluate, and now numpy array in the data type float, it's made and returned. Okay, that's the function. Now we begin here the three-dimensional problem, x0, x1, x2, and this line is making now three variables, x0, x1, x2, and vars will be this one. Okay, vars will include, okay, that one is the same as here x0 and x1 and x2. It is including all the variables. Okay, now f is defined by using these variables x0, x1, x2. You may think this is x, y, z. Okay, now we defined the quadratic objective function. Okay, by using Hessian, we get gradient and Hessian. Okay, these are the printing out to see if it is working well. And then now once we try to print out this Hessian, and for others, just I commented out. And here, now we are using the Newton method to get to solve the problem. Start with 0, and length of vars is 3, so it's a three-dimensional vector, and along with the 0 values is made, and that is x0 will include all the 0. For Newton method, the gamma, the parameter, can be 1. We'll do only 5 iterations. Now, for the Newton method, and gradient and Hessian is made over there, and we evaluate for given point x, and so that it is now numeric gradient, and then there is, after evaluation, there is a numeric Hessian. This is a metric, this is a vector. Okay, but for this setting, here now quadratic, so the Hessian will be constant. But I wrote down this one generally. Once it is not constant, then you will evaluate along with the x numeric vector. But anyway, it's not harmful, so that I put over there. Now, gamma is 1, so that this is here inverse of Hessian times gradient, and along with the negative, the gamma is 1. Now, okay, you should squeeze this one. Once you do this operation, then the result is, in fact, a two-dimensional the vector, so that it is the quantity is like a vector, one-dimensional vector, but is expressed as a metric, so that by using this squeeze function, you can get the one-dimensional vector. In fact, having 3 components for the problem is non-metric, and after applying this one, is a vector, and now updated and printing out, and then do 5 iteration. Let's see output. This is a first printout, the Hessian. Hessian is now this first row, second row, and third row. Now find the minimum by the Newton method. Start with 0, 0, 0. Now after one iteration, it converged completely, and from second, and now never change. So for quadratic optimization problems, the Newton method converges in a single iteration always, no matter what the initial point is. Here, the issues. The central issue with the Newton method is that we need to be able to compute the inverse of Hessian metric effectively. For many applications, the dimensionality of the problem can be of the order of 1,000 or order of millions. So computing the Hessian or its inverse is often impractical. Because of these reasons, the Newton method is well used in practice to optimize large problems. Luckily, the algorithm can still work even if the Hessian is replaced by a good approximation. So various quasi-Newton methods have been developed in order to approximate and update the Hessian metric. Okay, here, one of the most popular quasi-Newton method is so-called BFGS algorithm. That is named after these 4 people. And these 4 people published almost the same idea around a quasi-Newton method, and independently also in the same year. These papers are published so that we give this name BFGS, and we really deeply appreciate their contributions to the computational science. This is one very popular algorithm. Now we'll try to do something else. Okay. Now, as a quasi-Newton method, what we'll try to do in this project is to use a banded submetric of the Hessian. Okay, let's see here. Given a metric, consider a similarity transformation of form. So from A, if we can find some permutation metric, PA, P transpose, that's now transformed metric. Now, we assume there is a permutation metric such that for the Hessian is transformed into a banded metric, formulated in this way. Then, along with this banded metric, it's much easier to solve. It's not always possible. However, anyway, in many applications, the given metric can be transformed into a near banded metric. This one is copied from these people. And originally, the metric has these non-zero quantities like this. So it's sparse. However, almost every non-zero appears. Now, by using some transformation, usually this permutation metric and front multiplication is changing the rows, and back multiplication, that one will make a column change. Now, after applying this similarity transformation, the metric has that. So along with the permutation, this is the transformed metric. And we can now cut out and try to use only banded structure along the the main diagonal, then we try to ignore some outside of this band. Then the amount we can ignore is very small, so that this one will be almost same as the original matrix. So it can be a good approximation. Such banded structure can be applied for the Newton method. Okay, recall the Newton method. Newton method is formulated in this way. From the earlier iterate, we try to get here Hessian inverse and gradient. Okay, Hessian and gradient. That is the correction vector, and usually now gamma is 1. Now we focus on this portion. Let's try to use the notation y and for this term. Then it is the same as hy is g. So by solving this system, we can get y. Now assume, and we have some transformation such that this is a banded matrix or is banded approximation, some matrix. Then this is the same as that one. So start with PG. Then now G is the same as here HY, so PHY. Now H can be replaced by this term, so we have that. Now this one will be identity, and now B, PY. So if we focus on this one equals that one, then now we can solve this system quite easily. Start with B, and now this portion is the same as now V. So BV equal PG. Once we know this P, then now changing the order of right side, after changing the right side by solving this banded matrix, we can get V, and from V we can get Y quite easily. Here from this equality we multiply P transpose, then Y equal P transpose V. So we can get Y quite easily. So that's one of the technique to get this vector quite easily. We can get, once we can get banded matrix, small matrix, then we can get it exactly. However, once we have to discard some portion, then there will be a good approximation. But here in this project, we will not do this one. It takes time for you, so that we try to mimic this here, the technique. Okay, here is the objectives. Now define, okay, this is in your own way, you can do that. Define f sub 4 as a function of 4 variables having local minimum. So that is now 4-dimensional problem. For example, x0, x1, x2, x3. So you can define in a 4-dimensional problem, and now define 6-dimensional problem, f6 as a function of 6 variables having a local minimum. Now you have to get the minimum of the function, so you can use part of the program already I implemented in Python, and to solve the problem by using gradient descent and the Newton method. Now we consider another the method, and you have to implement another function for a quasi-Newton method in which the Hessian is replaced by its tridiagonal portion. or part of information of Hessian will be used there. That is H3. Let's call the tridiagonal portion H3, and the entries are Tij. Then Tij is the same as original the Hessian when now I minus j is less than or equal to 1, so that only tridiagonal will be the same as the original Hessian, but otherwise you put the value 0. So it is a tridiagonal approximation of the original Hessian. We call this method the banded Hessian method, which is a kind of a quasi-Newton method. So now you have two problems, F4 and F6, and three algorithms: gradient descent, Newton, and banded Hessian. Now you implement the code and compare their performances, and gradient descent, Newton's method, and banded Hessian. For the method, you have to set the parameter gamma as good as possible for each problem and each method. And while trying to understand the algorithm's convergence behaviors, for the Newton method, for the Newton method, you may set the parameter gamma equals 1 if the iterals are oscillatory or diverging, particularly for the gradient descent method. Then it is a good indicator that gamma is too large. So you have to choose gamma smaller. Compare the number of iterations and the total elapsed time. Particularly, try to count the number of iterations and compare those methods, and try to make a conclusion saying that which method is the best. When the problem size is much larger, for example, 1,000 or 1,000,000, then is it possible for you to conclude differently? So try to understand and try to observe the convergence behavior of this method, and then try to answer this question nicely. Okay, here is a note. And along with this note, I'll give you some hint or some requirements to all of you. Try to include the term and x0 times x3 for the 4-dimensional problem, and x0 times x5 for 6-variable problem. The reason I'm asking you this one is that this term appears in your the function, then now its corresponding Hessian will have a non-zero value at top right and bottom left corners, so that once you try to now use only tridiagonal, then that will be now eliminated, so that it becomes approximation. Okay. Now for undergraduate students, you may try to select the two functions f4 and f6 to be quadratic, so that the Hessians are constant matrices. So it is not depending on the variables. And quadratic, then after second derivative, that will become constant. Each entry will be constant. It's quite simple. But for graduate students, you should add at least one fourth order term and of the form, so that along with some coefficients, now for xi fourth order with a positive quotient. So you have to make the problem having a local minimum. Once it is negative, then and around there, maybe there's no minimum value. Probably the other way is organized. So they try to use always positive quotients for the power of one variable, and do not add any third order terms. Third term is now odd term, so that it will make try to make the function the origin symmetric, and so that you may have much more difficult situations. So that try to not to add the third order terms. Just try to add only the fourth order and second order. And now second order term will be now some xi squared or xi xj multiplication. Either way, you try to add those terms so that the problem will be simpler, and also it guarantees the existence of local minimum. For all of you, I want to say this one. Select the coefficients of square and quadratic terms larger than those of the mixed terms. That means that now x0 squared, x1 squared, x2 squared, and the quadratic term, for those terms, try to choose the coefficients larger than those of mixed terms, like x0, x1, or x1, x2. And for those, here the coefficients of these terms should be large. That will make the Hessian metric diagonally dominant and also symmetric positive definite. Without this one, maybe your problem may have no local minimum. Then you have a big problem. So that try to be careful when you set the coefficient. Okay. The banded Hessian submetric can be a good approximation, although a similarity transformation is not applied, because diagonally larger quantity is now given along the diagonal, so that even though you cut out and accept the tridiagonal entries, that here banded Hessian will be a good approximation. So we are mimicking the similarity transformation. Okay. Here is how to report. Start with a one-page summary, including your conclusion, and try to attach your whole code, and also include your comparison analysis with supporting results. Okay, this is your project, and you will work on it after spring break. Okay, thank you.